Hi everyone, and welcome to the flipped instructional recording for science and engineering. Be sure that you take notes during this recording and update your science notebook. You also want to be sure that you update the slide in your notebook with the title and the lesson number. So really quickly, I'll pull up the template. And I know my screen only shows a portion of it, but here we've got physical science. I put it in red just so you guys could see it better. Unit 1, and then this is 1.04, Intro to Science. I'm sorry, it should be just Science and Engineering. I didn't finish cleaning that up. So there we go. I just snipped the guiding questions in. Obviously, there's no room right here for me to answer it. So if you copy paste them in, if you use the little chart that's included in there, either way, it's fine, whatever is easiest for you. And then if you'll notice over to the side, I've duplicated several of the slides so that I don't fill one up and then need to duplicate. So remember, you're just right clicking and duplicating the slide so that it adds more down here. That way you have several as you get going. So mine all say 1.02, so you just have to remember to update that each time. All right, so as we take a look at science and engineering, the guiding questions are in there. We'll go through most of those as well. Bungee jumping must be exhilarating, and what could go wrong? Actually, a lot. So after you've watched a few people go, you might decide it's safe enough to try it. But what would you want to know if you were the first person to try it? So see if you can see this video. Sometimes in a recording, they don't play very well. So me being someone petrified of heights, I would never ever do that in a million years. But here are some things that you want to think about. Bungee strength, right? So the cord, is it strong enough to hold the jumper? That's important. So we know we've been talking about elasticity. We checked out that word last time. Is it too springy? Is it possible that the person's going to bounce back up and hit any part of that metal? So that would be really bad. Or is it not springy enough? Would they hit the ground or something like that? That would be really bad as well, right? So those are just a few things. So before jumping, you'd want to collect a lot of data to verify that you would be safe. So here are our lesson goals. There are quite a few in this lesson. You're talking about kind of setting up an experiment, just getting some of those terms in with you. So you're describing science as both a body of knowledge and the process and practices used to add to that body of knowledge. You're describing how advances in technology influence the progress of science and how science has influenced advances in technology. Hopefully you're able to explain that scientific knowledge is constrained by human capacity, technology, and materials. Explain that laws are regularities or mathematical descriptions of natural phenomena. So here think about like the law of gravity. Explain that theories are explanations for observable phenomena. So sometimes we create laws, sometimes we create theories about things. Explain that science theories are based on a body of evidence developed over time. Explain that a hypothesis is used by scientists as an idea that may contribute important new knowledge for the evaluation of a scientific theory. So one thing to remember is a hypothesis is most of the time incorrect. We can't solve everything, right, the first time we test it. Identify that the term theory, as used in science, is very different from the common use of it outside of science. So there is a different kind of definition there. Apply scientific ideas or principles to design, construct, and or test a design of an object, tool, process, or system. And finally, design a structure to serve a particular function. So remember, keywords, you want these in your notes as well. A hypothesis is a tentative answer or solution to a scientific question or problem that considers observations related to the original question or problem posed. It may be framed as a detailed question or statement. A theory in science is a scientific explanation that accounts for observations of many types. So basically, based on everything we know, we think this is an explanation for something, right? It could be proven otherwise as you gather more information over time. And then a universal law. It is a principle that is in effect always and everywhere. So the law of gravity is a universal law, right? It's in effect everywhere, except for when you go into space. So it's kind of interesting saying the word universe, space, gravity, all of that. So with that, hopefully you have those things down in your notes. And we're ready to move on. Sorry, my computer's moving a little slow, moving pages. All right, so again, the guiding questions that we'll be answering, what are some bungee design considerations? If you look back at that slide, you remember that you want it to be springy, but not too springy. So you could look back there to fill that in. Scientists' goals. What are engineers' goals? What is the difference between a hypothesis, a theory, and a law? So we've kind of talked about those briefly. How are science, engineering, and technology interdependent? And how do science, engineering, and technology influence society? So those are your guiding questions. And remember, if we go back up to this lesson, my mouse is doing something weird every time I change over. So that's 1.3. This is 1.4. This is where your guiding questions go. All right, so going on, we're getting into the lesson content. All right, so as we get into the lesson on science and engineering, we know that scientists build knowledge to understand phenomena. And I'm going to just pull up my PowerPoint and move it over so that I can see those questions and keep them in front of me as I work. That way we can answer them as we go. That's what I would encourage you to do. So as scientists, our goal would be able to understand physics so that we can explain and predict phenomena. So that is question number 2 in your guiding questions. What is a scientist's goal? And then a phenomenon can be something as simple as this. Objects fall to the ground when dropped. Scientists like Galileo observed this phenomenon and wondered why they fall and what else is true about falling objects. Galileo asked questions like this: do all objects fall at the same rate? As engineers, we'll use our knowledge of phenomena to design or evaluate solutions related to phenomena. So an engineer's goal, right, would be to design or evaluate a solution related to the phenomena. So Orville and Wilbur Wright, you've heard of the Wright brothers, understood physics, but they didn't study it to broaden our understanding of the natural world like Einstein. The Wright brothers applied their understanding to build and fly the first airplane. They were engineers and they used physics to design a solution based on physics principles. So physics involves science and engineering. And physics, obviously, one of the things we're studying in physical science. So a glider is similar to a plane, but it has no engine. A plane tows the glider into the air, releases it, and then it slowly glides back to the ground. Pan and zoom around the glider image. Think about how science and engineering are used to design in the designs so that the glider responds to force and motion. So this seems kind of scary to me. No engine and flying through the air. All right, so scientists work to understand physics. So we've answered questions 1, 2, and 3 so far. As scientists, we want to know what kinds of forces are at work on structures and what happens when the forces are not balanced. A scientist is concerned with making sense of the way gravity and friction work, how the strength of materials work together, and how those materials behave over time and under different conditions. For example, a scientist is researching building materials. He's studying how the steel behaves when it is compressed and pulled. He will record his findings and share them with others who may contribute to the body of knowledge with their own observations and experiments. So here we go with our fourth question, the difference between a hypothesis, theory, and law. So we're talking about that here. So scientists used hypotheses, laws, and theories to describe the universe. A hypothesis is an educated, testable guess that predicts how variables are related in an experiment or model system. It is often expressed as an if-then statement. A theory is an explanation about the natural world that has been repeatedly confirmed through observation and experiment and accepted by the scientific community. So already you can see a hypothesis is a guess. A theory is something that has been tested and is considered fact until it's proven otherwise, but an explanation about something in our natural world. And then a law is the description of the relationship between observable phenomena. So theories and laws work together to explain and describe the behavior of physical systems and the universe as a whole. So it talks about how, in guiding questions, how are science, engineering, and technology interdependent? So we kind of get into a little bit of that here. People have misconceptions about ideas, theories, laws, and hypotheses. So let's clear those up. A scientific theory isn't the same thing as the common theory that you hear people talk about in everyday language. When people say, hey, I've got a theory about that, they usually mean they've got an idea that attempts to explain something. Many people think hypotheses became theories and theories become laws, but that's not true. So collectively, hypotheses help form scientific theories, but they don't become theories on their own. Theories don't become laws because theories and laws are different things. Laws are statements that describe phenomena. Theories help explain phenomena. For example, and gravity is always a great example, we have laws of gravity that describe the way gravity works. And we have a theory of gravity that tries to explain how gravity works. The law and theory need to work together, but a theory doesn't become a law. Scientific laws are universal. So a universal law is a principle that is in effect everywhere at all times. An example of a universal law is the law of gravity. Any two masses that have a force of attraction between them. Physical scientists think that this law applies to any two masses in the universe. So gravity is universal. And when we talk about it being in space, it's a little bit different concepts there, but it is still universal. So in your study of physical science, you'll encounter many universal laws. Example of universal laws include the law of conservation of energy, the law of conservation of momentum, and Newton's laws of motion, which you'll learn about in future lessons. Engineers use physics to solve problems through design. Engineers are interested in using science to solve problems by designing solutions. Mechanical, structural, civil, and electrical engineers are all examples of engineers who are interested in using physics to solve problems. Packaging engineers consider which materials should be used to protect fragile items. Different goals. So a person can be both a scientist and an engineer, but the discipline of science and engineering have different goals. So remember, that's a question in the guiding questions as well. The goal of science is to broaden our knowledge base. The goal of an engineer is to design a solution to a problem. So if you had not written anything down in your guiding questions yet, right there's the answer for 2 and 3. Sometimes that problem might be very practical, like designing a bridge to get across a river, In other cases, the problem may really be an opportunity to design something that inspires people. So in this course, we'll continue to make sense of the world through physics. We'll focus on studying forces in motion, and then we'll apply what we know to create or evaluate our design solutions. Science, engineering, and technology are interdependent. Remember, this is going along with question number 5, which is asking how are they interdependent? As scientists work to better understand the universe, engineers apply new scientific discoveries to create new technology. New technology better helps scientists understand the universe, and the cycle continues. Okay, so you can see that means they are dependent on each other to keep evolving. All right, science, engineering, and technology influence society. And that's question 6 in your guiding questions. Sometimes the technology developed is used directly by people in society. Mobile phones are one example of technology that has had a large influence on society. Consider some of the technology that you use every day and how your life would be different without it. Think about the internet, computers, things that we're using right now. All right, so as we get into the last slide lesson here, this simulation uses blocks and springs to model jumpers attached to bungees. Each jumper has the same mass, but the springs are different. Evaluate the design of each bungee by dropping the jumpers from different heights. And jumpers want a long drop, but they don't want to hit the bottom. The jumpers are suspended from above foam blocks. So evaluate each bungee by lifting and dropping the jumper. Find a safe drop point and let the jumper touch the foam pit just a bit without hitting the ground below. So what are 2 design criteria that you need to consider? Okay, remember the jumpers want a long drop, but they also cannot hit the bottom. So if we look at A, we've got this spring here. Right, it says you pull them up to the top and drop. So they have a long drop, and they did touch the bottom. In B, if we pull it up to the same, remember that's one of the things, you've got to keep the drop point the same, and that's kind of hard to do here. But that one really hit the bottom hard. And then C, if we pull this one up and drop it, that one did pretty good. You had a long drop, sprang back up. We didn't really touch the bottom at all. So what's the best drop height for a bungee? So you can see, is it up here at this 90? Is it up here like at 70? So you're testing that. The best drop height is close but not over 50. Wow, that's over here. What is the best drop height for bungee B? So that was, the best, sorry, it covers up the question. The best height for bungee B, this one, the best drop height says it's 55. So you're putting it up here. And then the best drop height for C was 70, which is as high as you can go. So it says getting it up here and dropping it. So which bungee and drop height best meet the criteria? That would be B. All right, so as we get into the lesson review, we learned about science and engineering and society, and we've answered the following questions. We've covered this one a couple of times. So the goal of scientists is to build knowledge to explain and predict phenomenon. And engineers, their goal is to design or evaluate solutions related to the phenomena. All right, so that gets you all the way through 1.04, Science and Engineering.